Hi Emma, this video is especially for you, and I hope that you're feeling better. I'm going to be going through the first question that you sent me in this video to see if the platform works, and if it does, then I'm going to record the rest of them on separate videos. Alright, so let's start with the first problem. It takes 151 kilojoules per mole to break an iodine-iodine single bond. Calculate the maximum wavelength of light for which an iodine-iodine single bond could be broken by absorbing a single photon. Be sure your answer has the correct number of significant digits. Okay, so in order to answer this problem, the first thing we have to ask ourselves is, well, we have to translate kilojoules per mole into joules, and we have to also account for the number of moles. So if we want to figure this out, because we don't want a mole of iodine-iodine bonds, we want a single iodine-iodine bond, because that's what they asked us about. First thing we have to do is we have to get rid of the kilojoules, and in order to do that, we have to multiply by 1,000, because there's 1,000 joules in a kilojoule. So upon doing that problem, we have 151 times 10 to the third joules per mole. And now, in order to account for the amount of moles, all we have to do is divide this number by Avogadro's number, 6.022 times 10 to the negative 23rd. Upon completing this math, you find that our answer for the amount of joules is 2.51 times 10 to the negative 19th joules. Okay, now we have the number of joules that we see are required to break a single iodine-iodine bond. Great! Now all we have to do is we have to solve for the wavelength of light that it would take to do that, because that's what they asked us for in this question. I'm going to need to erase a portion of this, so if you need to, pause this video and write down the work, and then after that, I will continue on. Alright, I'm going to erase this, and I will leave the result that we got in our problem. Okay, we have the amount of joules, which is the energy. And we know from our formula, E equals hc over lambda. Lambda being the wavelength, h being the Planck constant, and c being the speed of light. We can now plug in, well, first we can rearrange this problem so that it's solving for wavelength. Wavelength is equal to hc over E. Now all we have to do is plug in the numbers, because we know h and c, those are both given numbers always. So h is 6.626 times 10 to the negative 31st, and we also have, to the negative 34th, and c is 3 times 10 to the 8th, and that's multiplied. And then on the bottom, we bring in our number here. So it's 2.51 times 10 to the negative 19th. In order to solve our problem, all we have to do is plug this math into our calculator, not forgetting to use parentheses in the correct places, and you will end up getting your answer of 7.919 times 10 to the negative 7th meters. Now, normally we have nanometers as our measurement for wavelength, and we can translate this into nanometers, and this number translated into nanometers is, I will draw the answer up here, the answer translated is 791.9 nanometers. And if we want this answer rounded to the correct number of significant figures, the significant figures that we would use would be 3, because they gave us 151, which is 3 sig figs, to start with. So the answer would be 792 nanometers. And that's the answer to question number 1.